All right then let's start with Chapter 1, Introduction and Preliminaries. I would like to start this lecture by explaining what it is that we want to accomplish by writing this book and by giving these lectures. And that is to share an elegant perspective that provides a powerful higher-level insight into first-order convex optimization methods. Historically speaking, the study of first-order convex optimization methods started in the 1960s and the 1970s. But the field at that time was focused rather on second-order convex optimization methods, which are much more effective at solving the smaller-scale problems that were of interest during that era. It was in the year 2000s that the increased computation power and the availability of big data that brought the first-order convex optimization methods into the mainstream. During this era, we, the authors, so Wo-Tao Yin and myself, entered the field of optimization and discovered, but we did not invent, the perspective that we mentioned, and we wish to share it through this book. So to put it more concisely, our goal is to present a unified analysis of convex optimization algorithms through the abstraction of monotone operators. The widespread modern use of first-order methods, in our view, makes this perspective much more relevant than ever for both optimization researchers and users of optimization. Our book and our lectures have a somewhat unconventional organization. The chapters are structured around the techniques for deriving and analyzing optimization methods rather than around the optimization method themselves. And through this organization, we aim to provide a structure to the theory and achieve intellectual economy in the sense that we analyze many optimization methods with a handful of mathematical concepts. And we hope the result is that our lectures and our book serves as a concise introduction to the theory of convex optimization algorithms. So to kind of flex on what methods that we can efficiently analyze through our unified viewpoint, these are the list of methods that we will establish convergence for each of the chapters. And not all chapters are about methods, so not all chapters are provided in this list, but for the chapters that we do analyze methods in, well, we establish convergence for a lot of methods, and I hope you will agree once you go along with us through these lectures and read the book that that our approach to analyzing these methods is very efficient. Now, to establish some context and also to explain why it is that you should study about first-order methods, and in particular why you should study this book or listen to these lectures, let's compare first-order and second-order methods. So second-order methods are second-order convex optimization methods use second-order derivatives or their approximations in the statement or in the implementation of their methods. And this was the focus of the field in the 1970s and 1990s, and that's because the second-order optimization methods are far superior when applied to smaller problems. They converge much more quickly to a higher accuracy solution. And these methods, comparatively speaking, require fewer iterations to solve the optimization problem to high accuracy, and often, when we can use the second-order methods, solving the problem up to machine precision is very much feasible. On the other hand, first-order methods are methods that can be described and analyzed with gradients and subgradients. And these first-order methods are the current focus of the field, and that is because these gradient-based methods are much more effective compared to second-order methods for solving large-scale optimization problems, including problems arising in machine learning. Now, first-order methods tend to have lower computational costs per iteration. So for larger problems, one iteration of a second-order method may be infeasible. So given a realistic amount of time, it may be impossible to execute even a single iteration of a second-order method, while a first-order method can execute many iterations and produce a solution to an acceptable accuracy. Another seemingly minor, but in my opinion, actually significant advantage of second-order methods is that first-order methods are extremely simple. So these methods often have a 2-line or 3-line description when you write it with the proper abstraction and with proper equations. And simple methods are, of course, simpler to implement, and also that's very much a practical advantage. And also, simpler methods tend to be easier to parallelize as well. So it's not always the case that simple methods are parallelizable and complicated methods are less parallelizable. That's not always the case, but it often is, or at least with a finite amount of effort that one can put into the programming. First, simpler methods tend to be, they would be quicker to implement and try out, and they do tend to be easier to parallelize. These two classes of methods, first-order methods and second-order methods, are usually not in competition, in the sense that if you're in a situation when a high-accuracy solution is absolutely necessary, then second-order methods should be used. And for small problems, you can just use second-order methods because there really is no reason to forego the high accuracy of second-order methods. So if you have a convex optimization problem, and if it's not that big, just install one of these second-order optimization solvers and then just call it, and you'll get a very high-accuracy solution. And these solvers are very robust. They're built very well over the many decades, so just use second-order methods if you can. But for large-scale optimization problems, one should use first-order methods and tolerate the inaccuracy. So if you have the mindset that I want to solve very large-scale optimization problems and I also want a very high accuracy solution, well, unless the problem at hand has very special structure, you're probably asking for too much. So for large-scale problems, really the only option that you have is so second-order methods are infeasible, so you should just use first-order methods for as many iterations as you can afford, and then whatever you get is what you get. And it's not going to be very accurate, but often in many engineering contexts, you only need a few digits of accuracy in your solution, so the inaccurate solution is often sufficiently good. Okay, now let's very briefly talk about convergence and convergence rates. So when you have an iterative algorithm, which and most algorithms in most algorithms in applied mathematics tend to be iterative. The total cost of a method is the cost per iteration times the number of iterations. To put it in a more programming context, if your algorithm consists of a for loop, then the total cost is the cost to execute one iteration of the for loop body times the total number of for loop iterations that you must perform, obviously. Now, the cost of iteration, when you consider the cost of iteration, what you do is you look at the algorithm description, or you look at the for loop body in your program, and you examine the computational cost of each line, each expression within your algorithm. And to analyze the number of iterations when we have an iterative algorithm, we must analyze the rate of convergence. So if the goal is to achieve epsilon accuracy, then how many iterations are required in order to achieve epsilon accuracy? Well, so this equation, cost per iteration times number of iterations is total cost. This is quite a trivial equation, and it's of course very accurate. But in optimization, we often make a further simplification. So methods in optimization are often compared with only the first term, with only the cost per iteration. And in fact, in the previous slide, when we compared first-order methods and second-order methods, we just made this very same argument. However, a method with a low cost per iteration has the potential to be efficient, but of course it doesn't have a guarantee to be efficient, because a method with a low cost per iteration may require an inordinate number of iterations, in which case the total cost will be very expensive. So considering only the cost per iteration is literally considering only half of the equation. But nevertheless, it's a useful simplification. So in our book and in our lectures, we will focus primarily on establishing convergence without paying much attention to the rate of convergence. In a more practical context, also in a setting where you actually need to have a good understanding of the actual total cost of your algorithm, then you would have to go further and go beyond just analyzing the cost per iteration. You will have to analyze the rate of convergence. But for the purposes of these lectures, for the purpose of this book, just considering the cost per iteration is going to be a useful simplification. So throughout these lectures and also in the book, we'll primarily focus on algorithm and analysis using monotone operator theory. And again, this will provide us with a streamlined approach for establishing convergence proofs. And in our lectures, in our book, we will consider results that fit this result. And when certain results don't fit this result, we will usually just not, we may discuss them, but we will not prove them. Now, these types of results that rely on monotonicity are often simple, or at least that's what we argue, but they are often not the strongest result. So that's because proofs based on monotone operator theory rely crucially on the monotonicity property rather than convexity as the key property. And this line of analysis doesn't lead to results involving function values. So for example, the classical gradient descent method converges under suitable assumptions, and the rate of convergence is 1 over k in terms of the squared gradient norm. But one can also show that the rate is 1 over k in terms of the function value suboptimality. So the first result, where we have the squared gradient norm converge at rate 1 over k, this can be proved with monotonicity. And if this is what you want to establish, then sure, that's good. But if you want to establish a rate on the function value suboptimality, and often in the context of convex optimization, the second result is the result people care about more. Well, in this case, you would need to use convexity, the additional property of convex functions called convexity, in order to establish this result. But based on the approach of our, the main approach of our book, well, that just uses monotone operator theory, so we wouldn't be able to show that. So convex optimization theory does go beyond the use of monotone operators. And to establish the best results, the strongest results, you really do need to go beyond monotonicity and also use convexity. However, just primarily considering monotonicity is going to be a useful first step. And in any case, the use of monotone operators, the use of monotonicity does play a central role in the analysis of convex optimization algorithms. All right, then, let's start with the preliminaries. I imagine that the majority of the audience of these lectures will be familiar with most, but not all, of these background material. The material that we will cover in the preliminaries will, roughly speaking, correspond to the contents of Boyd and Vandenberg Convex Optimization, chapters 2 to 5, and some background on subgradients and set value analysis, and also Rockefeller 1974 Conjugate Duality and Optimization. Okay, so now let's define some overloaded set notation. So a lot of standard notation defined for points, and here when I say points, I mean vectors. So we take notation defined for points and generalize them to sets. So for example, if alpha is a scalar, and then x is a vector, and a and b are subsets of Rn, and M is an m by n matrix, then alpha times a, well, we take all the vectors within A and then multiply by alpha and form the set. X plus a, well, x is a vector, a is a set. Well, we take all vectors in A and then compute x plus a and form the set with those results. The matrix M times A, well, we take all vectors from A and then multiply by M and then form the set. And then the set A plus B, well, we take all vectors from A, all vectors from B, and form the set with A plus B. In particular, the sum A plus B is referred to as the Minkowski sum. Okay, next let's consider the shared complement. So let X be a block matrix with blocks A, B, B transpose, and C. And the top left block A is an m by n matrix, m by n symmetric matrix. So the top left block has this form, so it's m by m. And then the top right block, B, is an m by n matrix. So the dimension over here is n, and the dimension of B transpose over here is n. And the bottom right block, C, is a symmetric n by n matrix. So the matrix X as a whole is an m plus n by m plus n matrix. When the matrix A is invertible, then we form the matrix C is C minus B transpose A inverse B, which is well defined when A inverse exists, and this is an n by n matrix. This is referred to as the Schur complement of A in X. Now, when the top left block A is positive definite, so here this strictly bigger symbol is used to denote positive positive definite matrix. So if A is positive definite, then the block matrix X being positive definite is equivalent to the Schur complement of A in X being positive definite. And when A is positive definite, then X being positive semi-definite, so this bigger than equal, weird squiggly bigger than equal, this is positive semi-definite. This is equivalent to the Schur complement being positive semi-definite. Now, we can also define the Schur complement of C in X. So here, so this is the Schur complement of A in X, but the Schur complement of C in X is defined analogously as this thing. So A minus B C inverse B transpose, that's the Schur complement of C in X. Now, with this case, if C is positive definite, then X being positive definite is equivalent to the Schur complement of C in X being positive definite. And if C is given to be positive definite, then X being positive semi-definite is equivalent to the Schur complement of C in X being positive semi-definite. The Schur complement is a useful tool to assess positive semi-definiteness of a block of a block matrix. Next, let's define the notion of Lipschitz continuity. So if we have an operator T that takes in as input a vector in Rn and outputs a vector in Rm, we say this function, this operator, is L Lipschitz or L Lipschitz continuous if it satisfies this inequality for all inputs x and y. So to describe this inequality in English, if we consider two distinct inputs x and y with a certain distance apart, then the output of the operator t at x and the output of the operator t at y, the difference of the outputs should be bounded by L times the difference of the inputs. So, and we say T is just Lipschitz, or we say T is just Lipschitz continuous without specifically specifying the Lipschitz continuity parameter L, if the operator T is L Lipschitz for some positive and non-infinite value of L. So if T is Lipschitz continuous with some value of L, we just sometimes say it's Lipschitz, and it's implied, and then that there exists some Lipschitz continuity parameter. So here are some properties of Lipschitz continuity. If an operator T is Lipschitz, then it is automatically continuous. And if an operator T1 and T2 are respectively L1 and L2 Lipschitz continuous, then the composition is L1 times L2 Lipschitz, and this is rather straightforward to prove. Now here, of course, in order to perform the composition, it is implied that the output space of T2 matches the input space of T1, but once we assume that, then this composition result holds. If T1 and T2 are two operators that have the same input and output spaces so that they can be added, and if T1 is L1 Lipschitz, T2 is L2 Lipschitz, then alpha times T1 plus alpha times T2 is, absolute value alpha 1 L1 plus absolute value alpha 2 L2 Lipschitz continuous. Let's define some notions of interior. So some basic closed set, open set type notation. The closed ball of radius r centered at x is written as bx comma r. So the center point is x, the radius is r, and this consists of all point y in the vector space Rn such that the distance from x is less than or equal to r. it's closed. It's therefore we have a non-strict inequality. We define so there are many ways to define what an interior is, but in this class we'll just and they're all equivalent in the case of Rn. But for this class, we'll define the interior of a set C and write it as int C to be the set of points within our set C such that you can have an open ball of non-zero radius, and this around the point X, and the closed ball will still be contained within our set C. The closure of a set C is written as a CLC, and the boundary of the set C is defined as the closure of C minus the interior points of set C. Okay, so the notion of interior closure closed set boundary is relatively standard throughout mathematics. But here we'll define the notion of a relative interior, which is not a universal definition, but it's used throughout convex optimization. So we define an affine set to be a set with the representation x0 plus v. So remember, so here we are using the set valued overloaded addition. So x0 is a vector in Rn, and v is a subspace of Rn. So x plus v, it means we take all vectors in the subspace v, add x0 to it, and then form the set with it. And an affine set, therefore, is a translation by x0 of a subspace v. Given a subset C of Rn, we define the affine hull as follows. And so we write it as Fc, and it is the set of vectors theta 1 x1 plus dot 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 theta k xk, where k is bigger than or equal to 1, k is finite, and the x's belong to the set C, and the thetas are they form a convex, not necessarily a convex combination, but they add up to 1. So the thetas need not be non-negative, but they must add up to 1. So this is one way to define the affine hull, but another characterization of the affine hull is that it is the smallest affine set containing C. So this is one definition of the affine hull. This is another definition of the affine hull. The relative interior of a set C is defined as, so it's written as RIC, and it's the set of points X within our set C, such that if we form the ball a radius r around point X, and the radius r has to have a positive radius, but the idea is that r is very small, and then we take the intersection of this ball with the affine hull of C, then this intersection lies within the set C. The relative interior of C of any non-empty convex set C is non-empty. So this is not an obvious fact, but if you try to prove it, it's not too difficult to prove. Actually, I take that back. It takes some convex analysis in order to prove this, but it's a useful result to keep in mind. So the relative interior of a non-empty convex set is non-empty. The relative boundary of a convex set is defined as the closure of the convex set minus its relative interior. So the relative interior, the definition expressed in that way is that it's necessary to make that, have that rigorous definition, but I think this picture better and essentially completely explains the notion of relative interior. So here we have the set S, and its equation is written in this way, but it doesn't really matter. What matters is this shape. So S is a subset of R2, and it's in particular a line segment of finite length. Well, the relative interior of S basically excludes the endpoints and just contains the open line segment between those 2 points. So you use the relative interior when a convex set resides essentially within a smaller dimensional space, a smaller dimensional affine space. You basically reduce your space down to the affine space and consider the notion of openness and closedness within that lower dimensional space. And the relative interior corresponds to the open set or the interior of your given set within the lower dimensional affine space. Okay, now let's establish some definitions regarding functions. So throughout this class, we will be using extensively use extended value functions that map a vector in Rn to the extended real line R union plus minus infinity. So note that here the function value can take value negative infinity. And the negative infinity part may seem unnecessary if you are, let's say, familiar with the formulation in Boyd and Vandenberg. So in that textbook in particular, functions are not allowed to take value negative infinity. But in this class, we allow functions to take value negative infinity as well, because some saddle functions, convex concave saddle functions, will sometimes take plus infinity and negative infinity as its value. So you'll see when we talk about saddle functions, you'll see why this definition is convenient and useful. So given a function, we define its effective domain as the points such that the output of the function is less than infinity. So in particular, if the function outputs negative infinity, then that's part of the domain. But positive infinity is not part of the points where the function output positive infinity. That's not part of the domain. We say a function is convex if it satisfies this convexity inequality for all points x and y and theta between 0 and 1. And here x and y are points such that that reside within the domain. And so here, because our functions are allowed to take value negative infinity, it's possible that we have an inequality between infinite values. So it could be the case that we have negative infinity less than something. In those cases, we follow the pretty much the obvious convention. So any finite value. So when considering this inequality, negative infinity is smaller than any finite value. Negative infinity is less than equal to negative infinity. Negative infinity is less than positive infinity. And any finite value is less than positive infinity. Positive infinity is less than equal to positive infinity. So to write that down, negative infinity less than equal to infinity, negative infinity less than equal to 3.5. So it's these kind of obvious conventions that we follow when we consider this inequality. We say a function f is strictly convex if this inequality is strict when x is and y are distinct. So if we replace this inequality with a strict inequality and we add the requirement that x is not equal to y, that's the requirement for a function to be strictly convex. And we say a function f we define a function f to be concave if its negation minus f is convex. And likewise, we say f is strictly concave if minus f is strictly convex. It's relatively straightforward to show that if a function f is convex, then its domain has to be convex. And that follows, that can be shown by a basic application of the definition of convexity. Throughout this class, we'll talk about differentiable functions. So given a function f that is potentially extended valued, well, we say that the function is differentiable. So the notion of differentiability requires that the function outputs a finite value at every point. So if we say a function is differentiable, that automatically implies that the function is not extended value. And furthermore, the partial derivatives exist for all input point x and all coordinates I. Okay, now let's define CCP functions, which is an assumption that we'll be making all the time. So we say a function f is CCP if it is closed, convex, and proper. So CCP means it means closed, convex, and proper. So the focus of this class is the use of monotone operators to derive and analyze convex optimization algorithms. So convexity is a key property that we will be utilizing. And to give you some background, convex optimization is a class of optimization problems that are much easier to solve compared to just general optimization problems. That's why we restrict our attention to convex functions. Well, in real life, plenty of functions are non-convex, and non-convex optimization arises all the time. So convexity is a strong but very useful assumption that we make. But once we assume convexity, then closedness and properness are rather minor technical conditions. So there are functions that are convex but not closed, and there are functions that are convex but not proper, but there aren't that many functions. Those functions are more commonly sort of a mathematical counterexample rather than something that occurs naturally. So plenty of functions are non-convex, but once we assume convexity, closedness and properness are relatively reasonable and realistically, and they're assumptions that realistically hold all the time. So in any case, I need to explain what those conditions are. So we say a function is proper if it is minus infinity at no point and it is finite somewhere. So if a function takes value negative infinity, then it can still be convex, but it'll just not be proper. And if a function takes value infinity, that's okay. Proper functions do take value infinity. But if the function is plus infinity everywhere, then that's not a proper function. A proper function f is closed if we say a proper function f is closed if its epigraph is a closed function. So the epigraph of a function is defined as a function in Rn cross, is a set in Rn cross R, where it consists of an input point x and a point above the graph. So alpha is a value above the function value, and we form that set. So epigraph is, well, the prefix epi means something above, right? So this is the set basically above the graph of f. So here are some properties of closed, convex, and proper functions. So again, most convex functions of interest are closed and proper, although there are plenty of functions that are non-convex. And a function is convex if and only if its epigraph is convex. So this is really the connection between convex functions and convex sets. Here, this word convex is referring to the convexity of a function, whereas here, this word convexity is referring to the convexity of this set epigraph. If a function is proper, then a function f be closed is equivalent to the function being lower semi-continuous. So lower semi-continuous is a property more commonly used in the broader mathematics community. So in some cases, some people might be more familiar saying lower semi-continuity. Although the word closedness is a much more shorter, concise word, so I prefer the word closed. And in any case, I'll usually just be saying CCP to just assume the three conditions at once. A function f is CCP if and only if the epigraph is a non-empty closed convex set without a vertical line. Okay, so here are here's a visualization. So this is a closed convex function. So the idea is that between these 2 points, the function has finite value, and then outside this interval, the function takes infinite value. So to draw this, to draw the epigraph, so this set, this is the set epi of f. However, this function, on the other hand, is a convex function. So if you think about what happens at the boundary here, it will still satisfy the convexity inequality because it will come down to infinity being less than any finite value. It will come down to that. But this is not a closed convex function. It's just a convex function. It's also a proper function, but it's not a closed function. Here's another example of a CCP function. So the function minus log, or to be more precise, what we mean is f of x is a piecewise function minus log of x for x bigger than 0, and then plus infinity for x less than or equal to 0. If we plot this function, the function looks like this, and this is a CCP function. So the function is it's never minus infinity. It has finite value somewhere. It's convex. Its epigraph is closed. And if we look at what the set looks like, it's a non-empty closed convex set. Okay, so CCP functions are the class of nice functions that we will primarily consider in this class. As a mathematician, it is interesting. I do find it interesting to consider what happens when some of these assumptions are dropped. So if we still assume convexity, but we don't assume closedness, we don't assume properness, what happens? Well, at a high level, what happens is that a lot of things work out sometimes, but some things don't work out at other times. So it takes once you stop assuming CCP, then what you basically you're basically considering the pathological cases of convex optimization, and you will end up having to reconfirm every single step of the analysis that we perform. And that's certainly possible, and you can write academic publications with it. But for the purpose of this class, we want to consider the nice case. We want to obtain simple statements. So we will be essentially assuming CCP entirely throughout these lectures. So if f and g are CCP functions, and then we want to consider when CCP-ness is preserved. Well, if we have a positive scalar alpha and A is a matrix, then A times f, that's a CCP function. And f plus g is also a CCP function, provided that, though, there's one condition, such that there exists an x such that f plus g is finite. It's possible that if f and g have non-intersecting domains, it's possible that f plus g becomes a function that is infinite everywhere. And if that happens, then the function is no longer proper, because properness requires that the function is finite somewhere. So the only scenario where f plus g becomes non-CCP is if there is no finite point. So we need to make this further assumption to ensure that f plus g is CCP. The function a composed with the linear operator, the function f composed with the linear operator a, is also a CCP function, provided that there exists an x such that ax is finite. So again, f composed with a is guaranteed to be convex, and it's also guaranteed to be closed, but the properness is not always guaranteed. It's possible that this is just infinity everywhere. So we need to make this further assumption that the function is finite somewhere, and in that case, then the resulting function, the composition, is CCP. Let's next define the indicator function. So given a set S, a subset S of Rn, we define the indicator function as we denote it with delta S. So delta S is the function evaluated at x. So delta S evaluated at x is 0 if x is within the set S, and it is infinity otherwise. So the indicator function is 0 or infinity. And the indicator function is useful because it allows us to convert constraints within an optimization problem into an explicit function. If the set S is a convex, closed, and non-empty set, then the indicator function is a CCP function. Let's define argmin. So argmin is the set of minimizers of a given function. So in terms of our notation, we write argmin of f. So f is a function. Argmin, it's the set of points x in Rn such that the function value at f is equal to the infimum of our function. When our function f is CCP, then argmin f is a closed convex set, but it can be empty. So f, again, argmin is a closed convex set, but remember the empty set is defined as a closed set. Is also defined as a convex set. So it's possible that it's possible that the CCP function has no minimizer, in which case the argmin can be empty. It's also possible that the argument is not unique. So there can be more than one minimizer of a given CCP function, and in this case, it will be closed and convex if the function is CCP, but it may not be a singleton. But if the function f is a strictly convex function, then the argument has at most one point. In other words, the argument of a CCP and strictly convex function will have 0 or 1 points. It has at most 1 point, so it is still possible. It's a strictly convex function. It is possible for a strictly convex function to have an empty argument. Let's define the notion of the subgradient. So we say a vector, an Rn vector G, is a subgradient of a convex function f at point x if this inequality is satisfied for all y. And the subdifferential of a convex function f at point x is defined as this set. So we write it as a del f at x. But this looks like a function evaluation, but really, when we provide x, we get a set. So here, the set consists of the set of g's, such that this inequality defining a subgradient, holds for all y. To put it differently, a del f at x is the set of subgradients of f at point x. So the set of subdifferential is a closed convex set. This is actually, if you want to prove this, then the proof goes as follows. So this set is an intersection of closed sets and closed affine sets, which are convex. So in the intersection of closed convex sets is a closed convex set. So that was a verbal description of how this is proved. But in any case, the subdifferential is for given f, for given f, and for given x is a closed convex set. Now here we use the words subgradient and subdifferential because this notion generalizes the notion of derivatives for differentiable functions. So a convex function f is differentiable at a given point x if and only if the subdifferential is a singleton. So if your function is differentiable, then there is only one subgradient. The subgradient is unique if and only if the function is convex function is differentiable. And if it's not differentiable, if the convex function is not differentiable at a certain point, then the subdifferential will not be a singleton. Another useful thing is that a point x star is a minimizer of our function, of our convex function, if and only if 0 is within the subdifferential. So this is really how the subgradient relates to the minimizing convex functions. So the problem of finding a minimizer of a function is equivalent to finding an x star such that the subgradient contains the point 0. So here is an example. The absolute value function, the function f of x is abs(x), absolute value x in one dimension, is a CCP function, and it is differentiable at everywhere except at this pointy corner. Well, so that means the subdifferential of f is -1 within this region. So here the function is differentiable, and its gradient derivative is -1. So the subdifferential is for these points is a singleton with value containing the value -1. And then in this region, where the function is again differentiable and its derivative is +1. So within this region, the subdifferential is a singleton with containing the value +1. Now here, though, the function is not differentiable. So we know from the previous assertion that the subdifferential is necessarily not a singleton. And as we see, the del f at 0 is this interval. So in particular, del f at 0 is equal to the set -1 to 1. So this is this interval drawn vertically. It contains the real numbers between -1 and +1. So if I add the axis labels, it's -1 and +1. Here's another example. So let's first look at the function. The function just has this shape, and then it has this pointy part here, and then goes up. As we can see, this function is differentiable everywhere except at point x2. Now at point x1, if we take the gradient of the function, well, in this case, it's a 1D function, so it's really just the derivative. But if we use the gradient notation, if we take the gradient and form a first-order Taylor expansion, we get this dotted line. So this is the first-order Taylor expansion of the function f at about point x1, and if we draw that, it becomes this dotted line. And this is a fact of convex analysis that if you have a differentiable function, if you form the first-order Taylor expansion, the first-order Taylor expansion is a global lower bound of the convex function. And as you can see, this dotted line, well, it's a lower bound of our convex function. Now at this point, at x2, the function is not differentiable, and there are many subgradients. So here's one possible subgradient, g1, and if we form something like the first-order Taylor expansion with the subgradient g1, we get this, and it forms and it serves as a global lower bound for our function. But if you think about what the definition of the subgradient is, a subgradient is by definition a vector such that if you form this thing like a first-order Taylor expansion, this thing serves as a global lower bound. That was the definition of a subgradient. So here we can visually see that this line serves as a global lower bound, and indeed that's what defines a subgradient. But because this point is pointy, well, we can have other global lower bounds. So here, if we take this point, if we take G2 and form this thing which resembles a first-order Taylor expansion, we get this line, and this line serves as another global lower bound touching point x2. And in fact, it's not just these two choices. We can imagine rolling this line around to different angles and getting many different global lower bounds at this point. And those global lower bounds correspond to the slope of those global lower bounds correspond to the subgradient at point of the function f at point x2. Next, let's define the normal cone operator. So let C be a closed convex set. Then the normal cone operator of C, which is defined as denoted NC at X, is an empty set if X is not within the set C, and it is this set if X is within the set C. And this turns out to be the subdifferential of the indicator function. So to clarify, this is subdiff of indicator function. So our primary use of the normal cone operator is really just as a notational shorthand for the subdifferential of the indicator function. So writing delta C is longer than NC, so that is why we will prefer the notation NC. But otherwise, we won't spend too much time really trying to understand what the normal cone operator is. The normal cone operator does have important meaning within the broader optimization and convex analysis context. And that's also a reason why I bring this up. We won't talk about the normal cone operator much, but you will become familiar with the notation and the ideas throughout this class. And then later on, if you encounter the normal cone operator in a different context, then you will recognize the connection. So we won't talk about really the meaning of NC that much, but I'll just show you one picture. So imagine we have this convex set C. So the set, of course, contains the interior as well. Now, if we evaluate the normal cone operator outside of the set C, it's just the empty set. If we evaluate the normal cone operator within the set C, it just contains the point 0. But if we contain the normal cone operator at the boundary of the set C, then we get basically the normal vectors pointing outward. So the NC evaluated at x2 corresponds to this direction. It points outward. And also it contains all scalings of that direction point, that vector pointing outward. But if we have a point if we evaluate the normal cone operator at a point of the boundary that is sort of not smooth, not differentiable, then the normal cone operator then contains many directions. And if we evaluate it here, it contains also many directions as well. More specifically, the meaning of this inequality is that, let's say we pick a direction like this, then and these blue lines are sort of directions into C. So these are directions into C, and this is, the red is a direction of and C. Then the idea is that if we take the inner product between these two, so if we take the inner product between the red direction and the blue direction, that comes out to be less than equal to 0, i.e. To put differently, so -1 times the red direction has angle less than 90 degrees with the blue arrow. So that was a very high-level, hand-wavy description of the normal cone operator. The normal cone operator, again, it's an interesting object in convex analysis. It is something worth trying to understand if you want to know convex geometry very well. But for the purpose of this class, we'll just write this definition down. Recognize that this is NC is equal to del delta C. So we'll recognize that this fact is true, and then we'll just move on. Okay, so we talked about the notion of subdifferentiability and subdifferentials, but when does a convex function have a subgradient? Well, a convex function f is said to be subdifferentiable at a point x if the function if a subgradient exists. So this says the subdifferential is non-empty. So this is the same thing as a subgradient existing. So the terminology is, I guess, slightly confusing because subgradient is an element of the subdifferential, and subdifferentiability means a subgradient exists or the subdifferential is non-empty. So the word terminology is slightly, but not, in my opinion, not too confusing. When a function f is CCP, then the subdifferential is empty if the point is not within the domain. So this is i.e. If f of x is infinity. So if you evaluate the function and the function value is infinity, then there exists no subgradient at that point. Okay, and then if we have a point that lies within the relative interior of the domain, so the point resides safely within the domain of our function, then the subdifferential is non-empty. So the function is subdifferentiable. The function has a subgradient at point x. So the issue of subdifferentiability, the question of subdifferentiability, is non-trivial only in the case where the point x is on the relative boundary of f. So to put it differently, the function f may or may not be subdifferentiable on the relative boundary of the domain of f. So here's a non-subdifferentiable example. So let's define the function f to have value infinity for negative values and to take value minus square root of x for a non-negative value, so positive values and 0. Well, if you plot the function looks like this, and at the point equals to 0, the function is not subdifferentiable. And that's because, well, if you think about what a global lower bound should be if you think about what the slope of the should be at this point, it corresponds to something like negative infinite slope. And infinite slope or negative infinite slope is not allowed when it comes to derivatives or subgradients. So the function is not subdifferentiable at this point, even though the function is CCP. And if you look at this function, the function's domain is, so domain of f is 0 to infinity. And so the relative interior of the domain of f is, well, 0 to infinity, non-including 0. And indeed, the function is differentiable. It's actually just differentiable, but it's also subdifferentiable everywhere within the relative interior of the domain of f. And also, when the function, when x is negative, then the function value is infinity, so the function is not subdifferentiable at negative inputs. So really, the question, the issue of subdifferentiability only becomes meaningful at the boundary, the relative boundary of the domain, when x is equal to 0. And in this case, the function fails to be subdifferentiable at this point. So the idea is that subgradients generalize gradients in the case of non-differentiable CCP functions. So, and several standard identities for gradients, they also hold for subdifferentials when certain regularity conditions hold. So here, del alpha f is alpha del f. So if I were to put in some parentheses, it would be, perhaps this would be more appropriate. So alpha times f is of course a function, and we can consider the subgradient of that function. And also del f. So here the alpha multiplies to a function. So here this is a scalar function multiplication, and then we take the subgradient of that. Well, here we take the subgradient operator and then multiply by alpha. So alpha times subdifferential of f at x. This would be a scalar set product. So remember, we are overloading a lot of sort of standard vector operations to sets, and that's going on. That's what's going on here. Well, so these two are equal when alpha is a positive scalar. Okay, so multiplying by a positive scalar and then taking the subdifferential is the same as taking the subdifferential and then multiplying by a positive scalar. Okay, next, if we define the function g as f composed with a, then del g is a transpose del f a under a certain irregularity condition. So if the function f is a differentiable function, then we can replace this with the gradient operator. So if f is differentiable, then we can replace this del with the gradient operators, and this would be the standard chain rule. Or perhaps not the standard chain rule, but the vectorized version of the chain rule for in the case where we compose a differentiable function with a linear operator. But we are not assuming that function f is differentiable. We're assuming that f is just a CCP function. This identity does not always hold, but rather it requires this regularity condition. So the range of A needs to intersect with the relative interior of the domain of f. This is a technical regularity condition. Okay, and the next identity is that del f plus g is equal to del f plus del g. So again, if f and g were differentiable, then we could just replace this with the dels with gradient operators, and this would be true because the derivative is a linear operator. But that's not the case here. So we have this identity holding most of the time, but this is not always true. So again, we need a certain regularity condition. We need that the domain of f needs to intersect with the interior of the domain of g. Or we could, because this is symmetric, we could also require that this would also be true if the interior of the domain of f intersects with the domain of g. But in any case, this is the domain, the other is the interior of the domain. So the first result, identity, just holds if alpha is bigger than or equal to 0. But the second and third identities require these regularity conditions. If we don't have these regularity conditions, then this equality then becomes an inclusion, a subset. And then this equality again also becomes a subset in the general case. But if we have these regularity conditions, then equality holds. By the way, the proof of these results is not that it's not that easy. So it does require some non-trivial ideas from convex analysis, and I would argue that the proof of these results is essentially equivalently difficult to the difficulty of these results. The difficulty of the proof of these results, I would say, is essentially equivalent to the difficulty of the proof of strong duality in convex optimization. So to put and again to put differently, yet again, these regularity conditions and these identities are very intimately connected with the notion of strong duality in convex optimization. So, and strong duality is not an easy concept. It's not trivial to prove, and neither are these results. But in any case, if you're interested, these are standard results that you can find the proof for in many convex analysis textbooks. But for the purpose of this class, we won't spend the time on the proof. We'll just move on and just use these, accept these as given identities. Okay, so throughout these lectures, I'll be using the word regularity condition a lot. So I better define what I mean. This is not a rigorous definition, but I should clarify it, though, in what sense I use it. Let's say we have a condition, if P, then Q. So we have this logical implication. Maybe we prove this result, or maybe this is obvious, but in any case, we have this logical implication from P to Q. Then if the condition P usually holds, whatever that means, then the logical consequence Q also usually holds. And we say, in this case, P is a regularity condition because P it usually holds, P is satisfied in the usual regular case. So, as an example, in the previous subgradient, third subgradient identity, we require that the domain of F intersects with the interior of the domain G. And this does not always hold. We can certainly construct examples for which this fails to hold. But this does hold in many situations. So we deem this, we consider it to be a regularity condition. So this condition usually holds, and therefore this identity also usually holds. Another regularity condition that we will discuss soon is the Slater's constraint qualification. So in convex optimization, strong duality is of course an important result, and strong duality usually holds. But what that really means is that there are several ways there's more than one way to establish strong duality in convex optimization. But one way is by assuming the Slater's constraint qualification, and the Slater's constraint qualification therefore because it usually holds in practice in most engineering applications. It's relatively straightforward to establish this Slater's constraint qualification. So we consider this to be a regularity condition. Next, let's define the conjugate function. So a conjugate function of F is defined in this way. So we form the inner product Y, inner product X, and then we do minus F, and then we maximize over the X variable, and F star is defined to be this supremum as a function of Y. And this conjugate function is, we'll be using this conjugate function a lot, and it's a very elegant object because, well, in general, it's not that nice, but when the given function F is CCP, then it's really nice because if F is CCP, then, well, F star is also CCP, and F star star is equal to F. Okay? And also, really the more important thing is that the grad F, so grad F is a mapping from Rn to Rn, and therefore you can define the inverse as a function. And when f and f star are both differentiable, then grad f and grad f star, and to clarify, the parentheses goes here. So grad f and grad f star are inverses as functions. So this is the most important identity, or this is the most important sort of notion that explains why conjugate functions are so prominent in convex analysis and also in convex optimization algorithms. The gradient operators become inverses of each other. Now, of course, the function f and f star are not always differentiable. So this statement is only for the special case. But more generally, the subdifferential of f is the inverse operator as the subdifferential of f star. So in general, so this gradient operators being inverses of each other, there is a more general and general version of this, and this version holds if f is CCP. So of course CCP is a strong condition, but once we assume that there are no further regularity condition, this just always holds. But what does this really mean? Well, we'll talk about this more in the next sessions, next chapter, when we define the operators, multivalued operators, and inverses of multivalued operators. Okay, next we define strong convexity. So we say a CCP function f is mu strongly convex if one of the equivalent conditions hold. So one condition is that f minus mu over 2x squared is convex. So this is one condition. Another condition is that this inequality holds for all x and y. So this condition is also called the strong monotonicity condition. So we'll see this again when we talk about monotonicity. But I want to draw your attention to this thing. So here, this is x minus y squared. This is just a scalar. But here, this is a set minus set, an inner product vector. So what I really mean when I write this is really this means u minus b x minus y bigger than equal to x minus y squared, mu, for all u in. So u is in partial f of x, v is in partial f of y, then x, y is in R n. Okay, let me clean this up. Okay, so I want you to get used to this type of set notation. So here we are heavily utilizing our overloaded set notation because we do a set minus a set, and then we're doing an inner product with that. And really the true meaning of it is this. But initially, if you're not careful, it's easy to make mistakes using this type of set notation, but once you get used to it, it's really useful because it allows us to express ideas that are not too complicated, but it allows us to express ideas in a really concise way. If we have a sort of set-valued expression and if we need, sometimes there's no choice but to be precise and not utilize this set-valued set value sort of overloaded notation, but when we can express ideas much more cleanly and concisely. Okay, so this is a second condition, and these actually first two conditions are equivalent. This is not obvious, but it's possible to show that these two conditions are equivalent. Another definition of strong convexity is that if the function f is twice continuously differentiable, then f is strongly convex if the Hessian of the function f has a spectrum lower bounded by mu. So this means this Hessian minus mu I is positive semi-definite, and that is equivalent to saying that the eigenvalues of this Hessian are bigger than or equal to mu. Okay, and now here are some properties of strongly convex functions. If a function f is mu strongly convex and a function g is convex, then f plus g is mu strongly convex. And so strong convexity is preserved under addition among strong convex functions. And I do want to clarify that strong convexity has nothing to do with differentiability. So a strongly convex function need not be differentiable, and in fact, we will see plenty we'll be using strong convexity on many non-differentiable convex functions. Next, let's define the dual notion smoothness. So we say a CCP function is L smooth if f minus L over 2x squared is concave. Another definition is that f is differentiable, and this inequality holds for all x and y. And this is also called the coercivity inequality. Another equivalent definition is that f is differentiable and the gradient mapping is L Lipschitz. This is also referred to as the Bailon-Haddad theorem. And finally, if the function f is twice continuously differentiable, then the function is L smooth if the eigenvalues of the Hessian are upper bounded by L. And again, these conditions are all equivalent. The terminology L smoothness implies once continuous differentiability because it requires that the function is differentiable and that the function, it requires that the function is differentiable and that the gradient mapping is L Lipschitz continuous, so in particular it's continuous. So L smooth functions are once continuously differentiable. But this is somewhat non-standard if we, in the context of the broad mathematics, because in other branches of mathematics, smoothness often refers to infinite differentiability. So I do want to clarify that. In this class, when we say a function is smooth, we mean it is once differentiable. In particular, its gradient mapping is L Lipschitz continuous. We are not, in particular, but we are not requiring infinite differentiability. And in fact, throughout this class, we will sometimes assume twice differentiability, but we will never assume any higher order differentiability. So let's try to visually get some intuition of strong convexity and smoothness. Informally speaking, mu strongly convex functions have an upward curvature of at least mu, and L smooth convex functions have an upward curvature of at most L. So here, and we can think of non-differentiable points to be points with infinite curvature. So here, if you look at this function, it has a consistent upward curvature. And this pointy point, we can think of this point to have an infinite amount of curvature. In any case, this is a strongly convex function because it always has positive curvature, and the curvature, if we were to extract it numerically, it would be lower bounded by a certain value mu. But this function is not smooth because at this point it has infinite curvature, so it's not upper bounded by a finite value. In contrast, this function is smooth. So its curvature here, it's a certain value. The curvature here is just 0. And the curvature here is, again, some positive value. But in any case, globally throughout the function, the curvature is upper bounded by a certain finite value, and therefore it's smooth. But because the function here, it has a flat region where the curvature is 0, the function is not strongly convex because a strongly convex function requires there to be always a strictly positive curvature, but this function here has 0 curvature. Also, the way I constructed this function when I drew this function is a once continuously differentiable function, but it's not twice continuously differentiable. And yes, to repeat the point, smooth functions in this class, in the context of convex optimization, refers to once continuously differentiable functions, but it's not infinitely differentiable. Okay, now let's discuss some relationships of strong convexity and smoothness, because indeed they are very much related. If a function f is mu strongly convex and L smooth at the same time, and yes, that's possible, then mu is necessarily less than or equal to L, because, well, that's pretty easy to just show. So the inner product between the difference of the gradients and the difference of the inputs, that's lower bounded by mu times x minus y squared by the definition of mu strong convexity, in particular the second definition of strong convexity. And then we can upper bound this inner product using the Cauchy-Schwarz inequality. And then, well, this term, the difference of the gradients, well, L smoothness, the third definition of L smoothness was that the gradient mapping is L Lipschitz continuous. So this norm is upper bounded by L times norm of x minus y. So we get L times x minus y squared as an upper bound, and then we cancel these out. So we get mu less than or equal to L. Okay, so if a function is both strongly convex and L smooth at the same time, then we have the relationship mu less than or equal to L. Strong convexity and smoothness are dual properties in the following sense. If a function f is CCP, then the function f is mu strongly convex if and only if the conjugate function f is 1 over mu smooth. So if f is strongly convex, then f star is smooth. If f star is smooth, then f is strongly convex. Okay, let's talk about convex-concave saddle functions and a saddle point. Let L, which takes in as input x and u, take in a length n vector and a length m vector. So x is length n, u is length m. So the two variables x and u, they don't have to be of the same length. And we let L output a real valued scalar or plus or minus infinity. We say the saddle function L, x, which takes in as input x comma u, is convex concave if L is convex in the first variable x while the u variable is fixed, and it is concave in u when x is fixed. We say x star comma u star is a saddle point of the saddle function L if it represents a Nash equilibrium. More specifically, unilaterally changing the value of u will decrease or at least not increase the saddle value, and unilaterally changing the x vector will increase or at least not decrease the saddle value. Next, let's talk about duality. So the notion of duality that we will discuss that we'll use in this textbook and also in this series of lectures is fundamentally not any different from the usual convex duality one encounters in standard convex optimization classes or textbooks. So the usual, the standard convex duality, the LP duality, conic duality, SDP duality, or Lagrange duality that one would learn from in, say, the Boyd and Vandenberg textbook, Convex Optimization, is equivalent to what we will use. However, the view is slightly different. The view that we will take is the conjugate duality view, sort of laid out by Terry Rockefeller in his textbook, 1974 textbook. And the idea is that the primal problem and the dual problem are, in some sense, symmetric, and they are both halves of a saddle problem. So let's take a look. Given a saddle function L, we define the primal problem generated by L to be the problem of minimizing this function. So this function is a convex function. So L is convex in U, and we take the L is convex in X, and we take the supremum over U. So this supremum results in a convex function in X, and we perform the minimization. So this convex minimization is referred to as the primal problem, and it is in some sense half of the problem of finding a saddle function of L because we're just performing the minimization over the variable X. In contrast, the dual problem is defined symmetrically. So in the dual problem, we maximize over u the inf of x of L comma u. So Lx comma u is concave in u. So when we take the infimum over x, this becomes a function, a concave function in u. So the dual problem is a concave maximization problem in the variable u. And when we take this viewpoint, then the idea is that we want to find a saddle function L that generates the primal problem of interest. So in engineering and science applications from which convex optimization problems originate, you usually are given a primal optimization problem. And what you do is the dual problem serves as a conceptual or a computational tool. It's a useful tool, but it's not the thing of interest. Really, eventually the thing of interest is the primal problem. And it is for this reason that the other views, the Lagrange duality, the conic duality, have a sort of asymmetric emphasis on the primal problem, because indeed, usually the primal problem is the problem that is given to us, and it is the problem that we care about more. And that's certainly, that's a very valid viewpoint, but for the purposes of these lectures, this more symmetric viewpoint is going to be more helpful. So here's an example. If we have a linearly constrained minimization problem, then so what I mean by linear constrained minimization is that here the primal problem is the form of minimize f of x subject to the linear equality constraint ax equals b. But instead of starting from the primal problem, the view that we take is that we start from a convex concave saddle function L. So our saddle function L looks like this, and then when we take the supremum over u, well, we get and once we perform some simplification, we get this primal problem. Now here, starting from the saddle function, if we take the minimum over x, then we get this thing. So the dual problem becomes maximize this concave function. And also, if this regularity condition holds, then one can show that strong duality holds, in particular that D star is equal to P star. Here's another duality example. So this one's called the Fenchel-Rockefeller dual. So we start with this convex concave saddle function, f of x plus u comma ax inner product minus g star u. So g star is a convex function in u, so minus g star. This makes this term concave. If we perform the maximization over u, then we get this function of x. So the minimizing this function of x, that is the primal problem. If we minimize the convex concave loss function over x, then we get this concave function of u. So maximizing this function becomes the dual problem. When this regularity condition holds, it's possible to show that D star is equal to P star. So when we define the primal and dual problems in this manner, then weak duality always holds. And weak duality is defined as a D star less than or equal to P star. And I should clarify that D star refers to the dual optimal value, and P star is primal optimal value. Okay, so let's do the proof. So for any x and u, well, the convex concave loss function L is certainly bigger than or equal to the infimum over x. Okay, and then so then we take the supremum over u on both sides, and then that taking the supremum on both sides with respect to u, that preserves the inequality. Now this term is just now it's a scalar. It's possibly infinite or possibly negative infinity, but it's in any case it's a fixed value. There's no the x and u variables have all been dealt with, but on the right hand side we still have the free variable x. So we take the infimum over x here, and taking the infimum on the right-hand side, that preserves the inequality. So that tells us that sup inf of L is less than or equal to inf sup of L. Now, this thing is the dual function, and this thing is the primal function. So if you think about this, the dual problem was maximizing the infimum of L. So this is the dual optimal value. And if you remember, the primal problem was minimizing the supremum of L. So this is the primal optimal value, P star. So we have D star less than or equal to P star, and we have proved weak duality. So weak duality always holds, and in particular, it holds even in the absence of any notion of convexity. Now, but in the convex optimization, the more interesting case is the more useful case is when strong duality holds. And strong duality is defined as the condition where D star is equal to P star. Strong duality holds often, but not always, in convex optimization, and regularity conditions that ensure strong duality are called constraint qualifications. In this textbook and in these series of lectures, we will define a term called total duality. So a total duality is basically a concatenation, a combination of three conditions. A total duality means a primal solution exists, a dual solution exists, and strong duality holds. So a primal solution exists, a dual solution exists, and the primal and dual optimal values are equal. And it turns out that total duality holds if and only if the convex-concave saddle function L has a saddle point. This means that when total duality is assumed, solving the primal and dual optimization problems is equivalent to finding a saddle point of L. And we will later see that total duality therefore becomes the regularity condition that ensure primal dual methods converge. Really the whole point of using the abstraction of monotone operator theory is to analyze constrained optimization problems more efficiently. And for constrained optimization problems, most splitting methods are primal dual methods in that they seek not just the primal solution, but the dual solution simultaneously. And for those problems, we will be assuming total duality in order to establish convergence. Okay, then let's show the equivalence of total duality and the existence of a saddle point. We'll first show the reverse direction. So we will assume that the saddle function L has a saddle point x star comma u star, meaning L of x star comma u star is less than or equal to L x comma u star and L x star comma u for all x and u. This was the definition of a saddle point. Then, L of x star comma u star is equal to the infimum of Lx with u star plugged in, and this corresponds to this inequality and minimizing the right-hand side with respect to x. And then next we have inf of x, L x comma u star less than or equal to sup u inf x L x u. Now this follows from defining this thing. Let's define this thing as, we'll use the symbol h of u. Then h of u star is less than or equal to sup of u h u. Because of course u star is one possible input. So if we take the supremum of h over all possible inputs u, that has to be bigger than or equal to just plugging in u star. So this is exactly just that. And then in the previous discussion of weak duality, we discussed why sup inf is equal to d star. Okay, and we also discussed how sup inf is less than or equal to inf sup. And we also discussed why that is equal to p star. Okay. Next, so the inf sup is less than equal to sup of u with x star plugged in. So again, this follows from essentially the same reasoning as before. So if we define this as, let's say, h tilde of x, then inf x, h tilde of x, is less than equal to h tilde x star. So that follows from, that establishes this inequality. And then finally, taking the sup, plugging in x star and taking the sup over u, that's equal to L x star u star, because, so this equality basically corresponds to this step. Okay, so we have L x star comma u star is equal to, we have a bunch of things in between, and that's less than equal to L x star u star. So this side is the same thing as this thing. So we have equality holds throughout. So these are actually not, these actually never become strict inequalities, and we have equality throughout. Okay, so this allows us to, so now that we've established these equalities, we can show the reverse direction. So here we had inf sup L is a sup u with x star plugin. So that's actually this equality. So this equality tells us that if we plug in, so this minimization, so inf x of this quantity, this is the primal problem, and then plugging in x star achieves the primal optimal value. So that means x star is the primal solution. So here we had a u star plugged in an inf x, so that's equal to sup inf of L. So we have this thing. So this thing corresponds to this. So supremum of u of inf x, that's the dual maximization problem. And then plugging in u star, if that achieves the same optimal value, then that means u star is a dual solution. So x star is a primal solution and u star is a dual solution. So that means a primal solution exists and a dual solution also exists. And then we had equality throughout. So that means d star is equal to p star. So we have this is an equality. So if d star is equal to p star, so strong duality holds. A primal solution exists, a dual solution exists, strong duality holds, so therefore total duality holds. Okay, now let's show the forward direction. So we'll assume total duality, and we'll assume that x star and u star are primal and dual solutions. So to reiterate, we assume that total duality holds, and total duality, when we are assuming total duality, we are assuming that a primal and dual solution exist, but we are saying x, we're denoting them as x star and u star. Then inf x Lx u star is sup inf Lxu. So this is this follows from u star dual solution. Again, this sup u, this is the dual maximization problem, and we plug in u star that achieves the optimal value. So that follows from the fact that the assumption that u star is a dual solution. Then we assume total duality, so that we're also therefore assuming that strong duality holds. So we have d star is equal to p star. So this is by strong duality. And then we have inf sup is sup u with x star plugged in. And again, so this inf of sup u, this is the primal minimization problem. And when we plug in x star, we have achieved the same optimal value. So this equality follows from the fact that x star is primal solution. Okay, and then we have L of x star u star. That's less than or equal to L x star, and then we take the supremum of u because, well, the x star is fixed, And then here we plug in u star, but here we take the supremum over all possible u's, so the right-hand side has to be bigger than or equal. Sup u l x star, that's equal to inf x l x u star, because we established that in this step. So this inf goes here, this sup goes here, we established the equality here. And then l x star u star, that's bigger than or equal to l x comma u star with inf x, because here the u star is fixed, but we take the infimum over all possible x. That has to be less than or equal to then just plugging in x star. Okay. So so we have l x star u star is less than equal to this, less than equal to l x star u star. So equality holds throughout, and then we conclude that sup u of x star is x star u. That's equal to l x star u star inf x l x u star. So to put it differently, we can also write L of x star u less than equal to L x star u star less than equal to L x u star for all x and u. So this tells us that x star u star is a saddle point. And that concludes the proof. Okay, next we have Slater's constraint qualification. So again, constraint qualifications are regularity conditions that ensure strong duality. So let's consider a primal problem of this form. So we minimize the function f0x subject to fi x less than equal to 0 and ax is equal to b. And this primal problem is generated by this particular Lagrangian. This Lagrangian is the Lagrangian that arises in the usual convex Lagrange duality. Slater's constraint qualification states that if there exists an x such that x is within the relative interior of the intersection of the domains of all the fi, and furthermore, the function value of fi is strictly less than 0 for I from 1 up to m, and also the x satisfies the linear equality constraint, then strong duality holds. So d star is equal to p star. And furthermore, is actually, if it is the case that d star is equal to p star, and that's, so if furthermore it is the case that the optimal values are not negative infinity, then a dual solution exists. So Slater's constraint qualification provides us with two results. One is that if the Slater constraint qualification holds, strong duality holds, but what is often forgotten is that if the optimal values are not negative infinity, then Slater's constraint qualification also guarantees the existence of a dual solution. This constraint qualification will be used throughout these lectures from time to time. Next, we have the proximal operator. So the proximal operator we'll be using the proximal operator as a subroutine very often throughout these lectures. So the proximal operator with respect to the function alpha times f is defined as prox alpha f, and this is an operator, so it takes in as input y, a length Rn vector y, and that's defined as the argument of this function, the argument with respect to x. So we have alpha f of x plus 1 over 2 times a norm of x minus y squared. So y is the input and x is the argument variable that we minimize with. And we define the proximal operator for CCP functions f and positive alpha. When alpha is equal to 1, we simply write that the proximal we just simply write prox f. The proximal operator is defined as an argmin. Therefore, it is important that we make sure that this definition is well defined. Well, it is well defined when the function f is CCP. So if f is CCP, then the prox alpha f is well defined in the sense that the argument uniquely exists. Let's prove this. So given a function, the ACCP function f, because the function is convex and proper, the domain is a non-empty closed convex set. And the relative interior of a non-empty closed convex set is not empty. Therefore, there exists a point x naught within the relative interior of the domain f. Previously, we made the assertion that CCP functions are subdifferentiable at a point within the relative interior of the domain. So a subgradient g of function f at point x0 exists. This allows us to construct the affine lower bound, which globally lower bounds our convex function by definition of subgradients. Now that we have this lower bound, then we can, so this function, which we refer to as f tilde is the function that is minimized in the argmin defining the proximal operator, and f tilde is lower bounded by this function that we refer to as h. So with the function h, the quadratic term 1 over 2 times x minus y norm squared, this term just remains the same, but our function f is replaced by the affine lower bound that we constructed with the subgradient g. Now the function h satisfies the property such that if the input x when the input x goes to infinity in magnitude, then the function value converges to infinity. Now, since f tilde is lower bounded by h, that means that property holds for the function f tilde as well. So what this tells us is that if we have a sequence xk such that the function value of f tilde converges to the infimum, because remember, when we consider the proximal operator, the proximal operator is defined as the argument of f tilde. So we consider a sequence xk that minimizes f tilde. And then this defines that this sequence xk has to be a bounded sequence because of this. So we can consider, since the sequence is bounded and since our underlying space is Rn, the bounded sequence has a convergent subsequence. So we take a subsequence, convergent subsequence xkj, and we denote the limit of the convergent subsequence as x bar. So the function f is lower semi-continuous, and that means f tilde is also lower semi-continuous. So lower semi-continuity of f tilde implies that the limit x tilde actually is less than equal to the infimum, the limit of this sequence, the limit of the function value of the limit of this sequence, which is in fact just the infimum of f tilde. Well, since the function value, since f tilde evaluated at x bar cannot be strictly less than the infimum of f tilde, that means that these two quantities are equal. So f tilde at x bar is equal to the infimum of f tilde. And this tells us that this limit x bar is indeed a solution. So a solution exists. Finally, because f tilde is strictly convex due to this quadratic term, the minimizer is unique. So that shows a uniqueness. We showed existence, we showed uniqueness, and that completes the proof. Here's an example of a proximal operator, and this one is known as the soft thresholding operator. The soft thresholding operator is denoted with S of x colon kappa. So x is considered the input, kappa is considered to be a parameter. And this can be written as the proximal operator of kappa times the L1 norm. And this function, this proximal operator has the closed form. So the soft thresholding operator acts on the coordinates separately. So we can just define the action of the proximal operator, the soft thresholding operator, coordinate wise. And the value is, well, if the action is if the input xi is bigger than kappa, then we reduce the value of the output value of x by kappa. If the input xi is less than is between minus kappa and plus kappa, we just output 0. And if the input xi is less than minus kappa, then we add kappa to the input and produce this as the output. Now I think, however, that the action, the of the soft thresholding operator is more concisely communicated by just simply looking at the plot. So this is the plot describing the action of the soft thresholding operator. And as we can see, if the input is between minus kappa and plus kappa, then we are basically thresholding the input to just take value 0. And then once it goes beyond a plus minus kappa, then the output is non-zero, but it is sort of shrunk towards the value 0 by magnitude kappa. Here's another example of the proximal operator, and this one is projection. So given a non-empty closed convex set, the projection is defined as, well, is denoted as pi c, and pi c of the point y. So this means we take the point y and project it onto the closed convex set C. That's what this notation means. And this is just taking the argmin over the points in C of the norm x minus y. Because this, the meaning of this argmin is we find a point within the convex set C that is closest to y. Now, if you think about this form, and also note that we can just simply add a square here without changing the meaning of anything, then it turns out that the proximal operator of the indicator function with respect to C is just the projection onto C itself. And since the indicator function actually just takes value 0 or infinity, in this case, the alpha value has no effect in the action of the proximal operator. So in this sense, the proximal operators generalize projections. The proximal operator is defined by an argmin. So generally speaking, evaluating the proximal operator is an optimization problem itself. However, many interesting convex functions have a closed form solution or a semi-closed closed form solution for the proximal operator, and therefore it is efficient to evaluate, and it is a useful subroutine. We will be using the proximal operator as a subroutine throughout these lectures, so it is important that the subroutine is efficient to evaluate. We say f is proximable, and this is an informal definition, but it's a useful definition. So we say the function f is proximable if the proximal operator with respect to f is computationally efficient to evaluate. Now, of course, not all convex functions are proximable, but a lot of very interesting convex functions are proximable. And there are several resources, there are several papers that catalog a very comprehensive list of proximable functions. So the idea of splitting methods is that we decompose an optimization problem, which presumably as a whole is not that simple, but we decompose it into smaller, simpler pieces. And these pieces are differentiable or proximable functions. And then once the pieces are decomposed, we operate on them separately. Okay, so that concludes the background and introduction and background section. So that's it for this lecture, and we'll continue with monotone operators and base splitting methods in the next chapter.